Okay, so it's finally time to give you a little proof sketch of Erdos stone Simonovits. Which I'm going to state, for now, I'm going to state it this way. For all graphs H and constants C that are positive, and sufficiently large n sufficiently large might depend on C and H. We have that the extremal number for H is in between these two things. And if you notice, these two things are essentially the same, except for here I have a minus C and here I have a plus C. So essentially what Erdos stone Simonovits is saying is that, basically if I just cover up this C, extremal number of H is roughly r minus 2 over r minus 1 times n choose 2 for large H. Oh, and by the way, r is the chromatic number of H here. So let's talk about the lower bound. The lower bound is easier. The lower bound is a lot like just Turan's theorem. If I make this graph, I have, of course, we have this divisibility issue where n might not be divisible by r minus 1. I'm pretending for right now, for what I wrote down, I'm pretending that n is divisible by r minus 1. Of course, if n is not divisible by r minus 1, then some of these need to be ceilings and some of these need to be floors just to make sure that this adds up to n vertices. So this is what I mean, and H is not a subgraph of this. Why is that? Here's an easy reason. This graph that I'm describing has chromatic number r minus 1, right? Because I can color all these the same color, color all these color number 2, and then, each one of these bubbles gets its own color, and that would be a proper coloring. And so that's a proper coloring with r minus 1 colors. But H has chromatic number r. A subgraph can't have a larger chromatic number than the graph that it lives in, right? If H were a subgraph of this, and this is an r minus 1 chromatic graph, then the chromatic number of H would be at most r minus 1, but it's not. So H is not a subgraph of this. Meanwhile, how many edges does this have? And this is where I'm going to be a little bit sloppy. This is an example of why this is called a proof sketch. Once again, I'm pretending that n is divisible by r minus 1. If n isn't divisible by r minus 1, then you have to round and you have to show that the error isn't too large and all of this. But let's not worry about rounding. If there's no rounding, the number of edges is about this. I'm just saying, basically, I have every edge possible except the edges within each bubble. So I took every edge possible, that's n choose 2, and then I subtracted the number of edges that would be in the bubble. So there's r minus 1 bubbles, and each one would have n over r minus 1 choose 2. And we're assuming that n is large, and for large values of n choose 2 is about 1/2 n squared. And r is fixed, once again, so n over r minus 1 is also large. So for this choose 2, I can basically say that's about 1/2 times that squared. And then if I estimate that, that's like r minus 2 over r minus 1. Oops, I forgot a minus sign down there. Times n squared over 2 edges, and that is more than this. Once again, n choose 2 is basically n squared over 2, so I'm comparing this number to this number, and this one's bigger than that one. Okay, so yeah, that's all there is for the lower bound. It's just observing that if I draw this graph, it doesn't contain H, and it has more than this many edges. Let's talk about the upper bound. Um, the upper bound is where we need sort of fancy stuff and Simonovits regularity lemma stuff. So for the upper bound, I have to show that if G is a graph that has n vertices and it has this many edges, then it must contain, or sorry, if it has more than this many edges, then it must contain H as a subgraph. So that's what we'll do. Suppose that G is a graph that has n vertices and has at least that many edges, or maybe I should say more, but at least is good enough. We're going to apply Simonovits regularity lemma. And this is a proof sketch, so I'm not going to be too picky about the details. Epsilon and delta are just chosen to be quote-unquote small numbers, and I'm applying Simonovits regularity lemma with this number epsilon. And I'll tell you what we're doing with delta in just a minute. But epsilon is the epsilon of Simonovits regularity lemma. So when I apply the regularity lemma, I'm getting an epsilon regular partition. So I get this partition of the vertices into V naught through VT. And well, yeah, okay. You can review the lemma if you forget what it says, but we get that partition. Okay, then I'm going to do something that I did before, which is after applying the regularity lemma, I'm going to delete some edges. I'm going to delete edges within parts, so if it has both endpoints in the same part, I'm going to delete it. Any pairs that aren't epsilon regular, I'm just going to delete all the edges between them. That's number 2. Number 3 is edges between parts of density smaller than delta. That's the purpose of choosing delta here. So I have this number delta that's quote-unquote small, and any pairs that have density lower than that, I'm just going to delete all edges between them. And then I'm going to delete all the edges that even touch V naught. If it has both endpoints or even one endpoint in V naught, I'm going to delete it. And this is very similar to something that we did when we were proving the triangle removal lemma. This is just a page of notes. This is elsewhere on e-learning. You can find it from a couple days ago. We applied the regularity lemma to a graph for a certain value of epsilon, and then we deleted those exact 4 things, and then we estimated the number of edges that we deleted, and we found that it was at most this. So I'm just going to steal that for our purposes now. The number of edges that we just deleted for us is at most this. And if you forget why that was, go back and review these notes. But I'm just going to steal that answer because I don't want to go through it again. So the total number of edges we just deleted from our graph is at most that much. And this gives us a little hint. Of course, I'm at the end of the day, this is a proof sketch, and I'm not exactly going to say what epsilon and delta need to be chosen to be, but here's what I want. I would like to choose it so that this number, this 5/2 epsilon plus 1/2 delta, I want to make sure that's at most C over 4. Why am I doing that? It's because this little bit C here is like the extra stuff that I have to work with. And I don't want to delete, or let me say that again. After I delete what I delete, I still want to have a little bit extra to work with. So if I were to estimate this, once again, n choose 2 is about 1/2 n squared. So the extra stuff that I have to work with is about 1/2 cn squared. The stuff that I deleted is less than 1/4 cn squared. In other words, the remaining graph, the number of edges that I have in the remaining graph, after I've deleted what I've deleted about at most half of the extra stuff that I had to work with. So basically C gets replaced with C over 2 here. So the number of remaining edges went from this, where I just have a plus C here, to at least this, where I have a C over 2 here. And I'm doing that just because we know, because of Turan's theorem, the extremal number of NKR. And we know it exactly, but more importantly, we know it approximately. The exact answer is, of course, annoying, because the exact answer, you have to talk about divisibility, and you have to talk about ceilings and floors. But the approximate answer is much nicer. The approximate answer is this: as n goes to infinity for fixed r, that this is the approximate answer, or when I write this symbol, once again, that means the ratio of this to this goes to 1 as n goes to infinity. And since we only care about large n, that's nice, because then it's clear for n large enough that this is, well, actually, well, yeah, okay. Since this is just approximate, we know that for n large enough, this is greater than this. Yeah. So, right. That means that after deleting all of the edges that we deleted, we still have a KR, because the number of edges that we have is larger than this, which is the largest number of edges you can possibly have without containing a KR. So it must contain a KR. And so right, this part of the proof has sort of paralleled the proof of the triangle removal lemma. So we have this KR, and how could this KR look? Given that this KR is still remaining after I've deleted what I've deleted, and I've deleted every edge touching V0, and I've deleted every edge within a part, so the only edges are going in between different parts. The only edges are going in between parts that are epsilon regular, and between parts that have density at least delta. So if there's a KR remaining, then there have to be R different parts, and this KR has to consist of one vertex from each part, and all of the pairs of these parts are all epsilon regular, and they're all density at least delta. At least delta. Now we apply the blow-up lemma. Can I find the blow-up lemma? Yeah. Here's the blow-up lemma. For all r greater than or equal to 2, for all c greater than 0, delta greater than 0, there exists an epsilon, such that for n sufficiently large, if we have r sets of n vertices each, so we have like v1 through vr, and all of the pairs are epsilon regular with density at least delta, then that graph must contain a k sub r of c. And right, so I have emphasized how much of a sketch this is, but we have a very similar setup here. I guess these don't all have n vertices. They all have the same number of vertices. So for your application, you would have to like replace n with however many vertices this is. Also, let's talk for a moment about choosing the quantifiers here. Because this brings in more restrictions of how one must choose epsilon and delta for this. Because this just says, like, if I fix an R and a C and a positive delta first, that there exists an epsilon that's small enough with respect to those choices. But that's okay. For what I'm doing, I can choose delta first, and I want to choose delta to satisfy this other requirement, so I'll make sure to choose delta so that it's, say, significantly, just choose delta so that I'll still be able to choose an epsilon to make this number smaller than c over 4. You know, choose delta to be c over 100 or something, just so that this isn't already killing us and making it bigger than c over 4. Then, once we've fixed a delta, and we have already fixed an r because h is given for this, and we have fixed a number c, which I will talk about later, then we choose epsilon. And epsilon needs to be, I've gotten a bit lost here. Epsilon needs to be small enough with respect to delta and r and c to apply the blow-up lemma, and epsilon needs to be small enough just to make sure that this isn't bigger than c over 4, which we can always choose a small epsilon if we want. So this is doable. And by the way, about this C, I'm making this a capital C for the blow-up lemma. The statement of the blow-up lemma has a lowercase c in it. I'm calling that capital C, not to get confused with what I'm calling little c. So by the blow-up lemma, this graph contains k sub r of c. In other words, it's a complete multipartite graph with r parts and c vertices in each part. In other words, you can find c vertices in here, c vertices in here, c vertices in each one, such that this set of c vertices is adjacent to all the c vertices here, all the c vertices here, all the c vertices here, and so on. It's like if you restrict it to just these c vertices, just these c vertices, just these c vertices, then it's a complete multipartite graph. And then that's what the blow-up lemma gives us, whatever c is. And, well, now I'll tell you what c is. We're going to let C be the size of the largest color class in a proper R coloring of H, because, actually, maybe I'm getting ahead of myself. The point is, we're trying to show that this graph contains H, right? We're talking about the extremal number of H, and we're assuming that this graph has a certain number of edges that we're claiming is going to guarantee that it contains H as a subgraph. So why am I talking about how it contains this as a subgraph? It's because this contains H, at least for a specific value of C. And I'm claiming that C is just the size of the largest color class in a proper R coloring of H. And that's not too hard to see if you think about it, actually. Imagine a coloring of H. We know that there's a proper R coloring of H. So if I draw H this way, where I draw all the vertices of color number 1 here, and I draw a bubble around them, then I know that there's no edges within here. And then I'll put all the vertices of color number 2, and I know that there's no edges within here, and so on. So I'll arrange them by their color class like this. And there's some edges in between, right? Maybe not all of the edges in between, but there's some of the edges in between. All I know is that 1 does not contain any edges, 2 does not contain any edges, and so on. And then that's, yeah, so then I'm claiming that that is a subgraph of this, which is just, you have R parts, just like these R parts. Each part has C vertices, and this is why I let C, basically I let C be big enough so that C is larger than any of these sets, or it's as large as the largest one, I should say. And then this graph has all edges in between and none of the edges within. But that's okay. I'm just claiming that this is a subgraph of this, which it is. This has none of the edges within parts and maybe some of the edges between parts. This one has all of the edges between parts and none of the edges within parts. So this one is a subgraph of this one. So there it is. We found a copy of H in the graph G.